This is a live Wi-Fi traffic visualizer. Every dot you see here is a Wi-Fi packet sniffed out of thin air. And today I'm going to show you how I made it using Rust on an ESP32. I know this isn't my usual crazy tech project, but trust me, it's going to be just as fun. It all started when I bought my first 3D printer, an old S1 Pro for $100. After modding it with Clipper, I started brainstorming cool projects. And then I remembered this, a NeoPixel display I've had for 5 years, but I barely used. It was time to give it a proper home. So the idea, a desktop Wi-Fi traffic visualizer. The workflow is pretty basic. First, we're going to create a 3D case for the LED panel. We are going to print it out and assemble it. Then we'll figure out how to capture Wi-Fi packets, then visualize them in real time. Easy, right? Normally with ESP-IDF, I can probably do the coding in less than an hour. But that wouldn't be so fun, so let's make it harder. Instead of a language I already know, I'll use Rust for this project. Just simply because it's so hyped and I haven't touched it ever before. Since many of you ask how I learn new things, I'll show you how I figure this out step by step. First, obviously, let's learn Rust. So I just spent a whole day reading the Rust programming book in order to learn Rust. I went through most of the chapters, but I skipped the project chapters and also the chapter related to functional programming, since I don't do that a lot. And I have to say, Rust is an amazing language. It's a surprise. It's a pleasant surprise to me. Every aspect of Rust is thought through carefully. For example, the concept of ownership passing is an elegant yet very intricate way of memory management. In C++, I already love handling pointers. I love heap management because, everything I want to do, I got to do it myself. That way I understand how my code works down to the very little details. But of course, when the project becomes bigger, more complex, errors happen everywhere. I can't, prevent it. It's just a human thing. Then comes things like Java garbage collector, which of course I'm not saying I hate, it's just that I can't understand sometimes what happens and what not. It's just not deterministic, you understand? It's easy to write though. There is a solution for this, which is resource allocation or acquisition is initialization, which is basically a technique in C++. I just learned it today as well. But it's basically tying an object lifecycle to its scope lifetime. And in Rust, they do it on the language level for you, which is so cool. It's still deterministic. And at the same time, it has zero overhead, as far as I understand. Please correct me if I'm wrong in the comment section. So cool. And though there's some weird thing that I didn't quite grasp. It's just weird. Like how Rust handles their enums as unions. What? They are enums. Why are you treating them like unions? Or like how futures work in async await of Rust. It's very cool. It's just weird to wrap my head around. Now, I would be lying if I learned Rust by simply reading a book and doing some exercises. Every theory that you learn has to be paired with practical projects, which is what we're going to do next. The first project we're going to do is enabling Wi-Fi promiscuous mode on this ESP32. Now, if you don't know what Wi-Fi promiscuous is, then for every single Wi-Fi device, of course, you can listen to any packet that is sent over the Wi-Fi radio, right? But by default, on your device, this is disabled because why would you want to listen to every packet on the network, especially when they're encrypted? You only want to listen to packets that are designated to you, right? Because only you have the ability to decrypt it. Now, in our case, since we want to build a Wi-Fi traffic visualizer, sniffing all the packets even from other networks is very important to us because we want to see how congested the network is. And that's why we need promiscuous mode, which enable us to see every single packet. Now, this was supposed to be a very trivial task, as you would imagine, because as you can see right here, there is a Wi-Fi sniffer example in the ESP-HAL. However, this thing drove me quite crazy because it's outdated, guys. It's freaking outdated. So I have to spend the last hour reading the source code of this ESP Wi-Fi crate in order to find what has changed. And for example, as you can see here, this function that lets you create a Wi-Fi controller and a Wi-Fi device, it has a function called new, which takes the Wi-Fi controller and takes the Wi-Fi peripheral. But in the new version, it takes here. There isn't a new function. It's now new with mode, and it takes these things. The added difference is this Wi-Fi station device, which is an unit struct in Rust, which just basically means, yeah, you're in Wi-Fi station device mode. And what that saves us is basically here, there's an added line that says set mode Wi-Fi station device. Now we don't have to do that anymore. And then the flow kind of doesn't change from there anymore. So we still have controller start, same as there, a sniffer, a set promiscuous mode, and set receive. This is a callback. So we have this callback for every single packet that is received by our Wi-Fi device. And you can see here, I'm just printing this out, packet received, and I'm showing the packet length. And there is a terminal show of this. As you can see, this is every single packet that is received by the Wi-Fi device on this ESP32. And you can see it's a varying length. I believe that the small ones are just like beacons packets. And this is of every single Wi-Fi network in our vicinity. So it's not necessarily the one that we are connected to, nor does the code connects to any Wi-Fi, as you can already see. So the next part of our project is going to drive these WS2812 LED matrix display from the ESP32 using Rust. And yeah, at first I thought this was a rather trivial task, because we must have crates which support this, right? But no, it was not a trivial task. It doesn't come from the fact that there isn't crates that support this. For example, this is esp-hal-smartled LED, which is a crate officially made by esp for doing this. And there is also this WS2812 ESP32 RMT driver, which used the RMT peripheral of the ESP32 to drive the LEDs. But here's the thing, guys. They are outdated as well. And the documentation is basically non-existent. So I, again, have to figure it out from the source. And my God, I swear to God, guys, people at esp, please, if you're going to release the software without properly testing it and properly documenting it, then why do you bother releasing it? Oh my God, I mean, you're a big company. You're a lot like an indie developer like me. And even for me, I write my documentation good. So please spare me the pain. Oh my God. But anyway, I was able to make it work, as you can see right here. And it's using the RMT channel on the ESP32. Now, as an addition to this, I'll also show you how the actual data transfer protocol of this LED works with a logic analyzer. So in order to give you a in-depth understanding of the LED transfer protocol, which is used in this LED display, I will show you the channel information of it. So what we're having right now is a sequence of 3 LEDs, which is displaying red, green, and blue. And this is connected to the ESP32 and is driven by GPIO 13, which I'm monitoring with a cheap logic analyzer from China. Why not? Okay, and you can see I've already recorded the data on screen, but just for the sake of it, I'm going to record again. And yeah, you can see there's a pulse of signal over here. And if I zoom in, I'm going to see the channel data. Now, in order to make sense of this, we have to pull up the data sheet. And yeah, the encoding is very simple. So as you can see, it's the same as what we have gotten in our matrix. We have 3 LEDs in cascading connection. So the output of the first LED goes to the input of the second LED, and so on and so forth. And as you can see in the diagram or graph or whatever, yeah, you can see the 0 is encoded, or every single data is encoded in the same amount of period. And for the 0, then the high is going to be less than the low time. And for the 1, then the high will be more than the low time. And for the reset, then everything is just going to be pulled down. Now, of course, there's strict timing to this, but yeah, just for basic understanding, and that's all right. And as you can see here, if there is a configuration of 3 LEDs, then the first data cycle will send, for each LED, 24-bit. So 3 bytes representing 3 colors RGB. And after these 3 bytes are sent, and the next 3 bytes for the next LED is sent, and until there's no more LED in the chain, then there's going to be the reset code. And the ordering of the color is like this. So the first color that's going to be sent is green, then comes red, and then comes blue. Now, as you can see in our LED, the first is red. So what we'll expect is for 8 0 pulse, and then 8 1 pulse, and then 8 0 pulse. That's what we should expect, right? And as you can see over here on the graph, whatever, and you can see it being this. So this is the red encoding. You can see 8 0 pulse, 8 1 pulse, and then 8 0 pulse, and that's for red. And the next one in the chain is green, right? So what we would expect for it to be is that 8 1 pulse right next to it. And you can see that right here, 8 1 pulse. And this encoding is used to drive all the LEDs in this huge LED panel, which, if you can already spot the problem, then yeah, these kind of LEDs is not suitable for driving large LED walls. We have gathered all the components necessary for this project. Now our job is to combine all of this to make a Wi-Fi traffic visualizer. The basis of this is pretty simple. We have an array of LEDs. At first, this array is completely off. As soon as a packet is sniffed by the ESP32, a random LED is going to be lit on. The more packets received, the more LED are going to be turned on. Over time, we are going to want to turn off some LEDs to clear up the panel. We do this by a cooling and diffusion process. The white LED is going to be treated as a spontaneous heat source. As it cools down, it dissipates heat to its surrounding. For example, if this LED is 255 degrees at step 0, then at step 1 it will cool down to 200 degrees, while its neighbor heats up to 50 degrees. For the visualizer to look like the animation from Matrix, the surrounding is confined to one column only. The concept of diffusion is inspired from the fire simulation from Kriegsman on YouTube. Instead of making each packet spawns a heat source, I calculated the number of packets per second and the number of bytes per second. This controls the probability that a heat source is going to be spawned. The higher the throughput, the higher the probability something is going to pop up on the screen. Thanks to all of this, we have a Wi-Fi traffic visualizer on the ESP32 with Rust. So this is the end of the project. As always, I leave all my code on GitHub. You can find them down in the description. This video is quite different compared to the other videos on this channel, so if you have any feedback or any question, just leave them down below in the comment section and I'll be happy to have a look at them and answer them. Have a nice day, and yeah, subscribe and like this video if you enjoy it.